Hello, my name is Thomas. I'm a PhD student from the University of Leuven in Belgium, and in this short pitch, I will introduce you to our methods on how to calculate utilities for a controller on a quasi-passive hip exoskeleton using tools from the reinforcement learning community. Before delving into the methods themselves, let's first take a look at the exoskeleton that we are working with. In the video, you see me wearing the exoskeleton. This exoskeleton provides an extension hip torque such that it can support users when picking up objects from the ground. The support is provided by a parallel spring mechanism mounted on each side of the exoskeleton. However, we call this exoskeleton a quasi-passive hip exoskeleton because the parallel spring mechanism can be actively engaged or disengaged using a solenoid mounted on the side of the exoskeleton as well. Apart from the solenoids, we also mounted sensors on the exoskeleton and more specifically encoders that allow us to track the hip flexion angles of a user during his or her movement. The main decision that the controller of this exoskeleton has to make is whether to engage the support mechanism or do nothing, since we only want to engage a support mechanism when a user is really lifting an object from the ground. To do so, we have implemented a controller that works in two steps. In the first step, we will try to recognize an ongoing motion. To do so, we first learned offline a number of probabilistic motion models, which we can then use online to estimate probabilities of an ongoing motion. In the second step, we will try to make a decision, and we make a decision based on an expected utility or an expected reward of engaging the support mechanism. However, to calculate these expected utilities, we first need to calculate utility functions offline. In the end, the controller will decide to engage the support mechanism when the reward or the expected utility for engaging is larger than the expected reward or expected utility of doing nothing. The main focus of this contribution is on how to calculate the utility functions. To do so, we start from the behavior of the exoskeleton and we write it in terms of states, transitions, actions, and rewards. This will lead to a set of equations, and we can then use the value iteration algorithm known in the reinforcement learning community together with some model data to arrive at reward functions or utility functions that belong to the different actions that the controller can take, which is engaging or not engaging or engaging only one side of the exoskeleton. These reward functions are then used by the controller and are queried by the controller to evaluate the expected utility or expected reward. In this way, we hope that the controller only engages when a user really wants it to. Thank you for your attention.